I was watching a video by David Picchiuto of Make Something where he demonstrated the strength of some brazed aluminum joints. His test piece was something like this, and he put it on the floor and stepped on the middle of it, and the middle part here bent before the joints here broke. And it didn't break until he actually put it against the floor and tried actually torquing this apart.
Yeah, it's just bending. All right, so yeah, the joint is starting to break right there.
So his first test actually only put the joint under shear force, and that doesn't break the joint nearly as much as putting it under a bending moment. So I offered to run some tests on his joints, and he sent me some samples. In fact, these are the samples that he sent me. So I want to test one of these samples under bending moment by holding this part fixed and applying the force here, and another one more under shear force by applying the force very close to the joint. So I need some means of holding this part very rigidly, and what I've come up with is this here with a channel in it, and there's a block screwed onto the end that this slides onto to hold it here, and then another thing that goes in here, and that prevents it from sliding against this part here. And this mounts onto my testing apparatus like so. Now I expect the force required to break this joint by shear to well exceed the 300 pounds of my bathroom scale, so I've come up with a lever arrangement. And this is my lever, and this part is 1/4 of this, so 4 times as much force will go onto here as onto here, and that way the bathroom scale will get 1/5 of the total force that I'm applying. And I've got these pins here to make sure that I know exactly where the force is being applied. And then this hydraulic jack goes on here. The jack itself sits on this piece of half dowel to make sure I know where the force is applied. I'm going to put a piece of dowel in here to soften where I'm pushing on here, but even so I'm still applying a fair bit of bending moment just over this distance here. So to try to neutralize that, I'm going to support the end of this with this arrangement here, and that prevents this from getting pulled up. And I've just had an idea to loosen this screw so that way this part can tilt on here a little bit, which means combined with the support back here, I'm really applying pure shear force to this joint. So let's crank this up and see what happens. I'm reading the pounds off the scale, so 10, 20, 30, 95, and my dowel is starting to get crunched a little bit. 95, 100, so that's actually 500 pounds pushing on this joint right now in shear. 100, 130, this might make a hell of a bang when it pops. 130, 135. Now my jack is touching this part here, so I think I'm going to have to reposition it. Oh yeah, so this clamp was starting to let off a little bit. So let's try that again. I may not need to reposition the jack. And let's crank that straight up to 100. 110, 120, and it's not touching here. Oh, this is letting up a bit. Okay, I need a bigger clamp. 120, 130. If you look in here, it's actually pulling apart right here, and it's bending a little bit here, so it's actually still bending moment that's mostly failing it. And also this part is bending a little bit too, so you can see it's opening up a little bit here. And also this has come out far enough that this screw is now tight against here, and this is bent a little bit here. So I'm actually still applying bending moment. It is still failing from bending moment across just this little bit of distance here. I've added this reinforcement here to make sure this part doesn't bend, and I've backed out the screw a little bit and moved my jack a tiny bit. So let's crank this up again and see what happens. Okay, that's 80. Whoa! Okay, that broke. For my previous test, I had the jack about 1.5 centimeters from the edge here. Now I've got it 11 centimeters from the edge and unsupported because I actually just want to bend this part. And I got rid of the lever arrangement because I'm pretty sure this is going to take a lot less force. Okay, now cranking very slowly. 20, 25, 30, 35, 40. I didn't quite get to 45. Okay, so we got to about 45 on here. And remember, this is actual force, not 5 times force as before. Even if you adjust for the fact that this lever arrangement here took up some of the up force that was applied here, perhaps as much as 5% of it, I still had over 600 pounds of shear force applied here before the previous one broke, whereas applying the force here, I didn't even get up to 40 pounds before it broke. So if I extend this test joint a little bit by putting these two pieces in here, it should take even less force. So let's see if I can break this one just with my little finger. Let's see. Broke it. I suspect the joint that broke at just 45 pounds cantilever force was the weakest of the 3 samples that Dave sent me. I bought some brazing rods to try to braze some of these back together to do some more tests, but with a propane torch I just couldn't get enough heat, and then switching to a MAP gas I just couldn't get a decent joint going. I just didn't have the patience to try to make this work. These brazing rods are really more meant for patching holes, and for actual joining pieces together I think TIG welding will be easier, quicker, cheaper and faster, as long as you have a TIG welder. I don't have one. On David's coffee table, I'm sure it'll be alright because 8 joints would have to break simultaneously for the legs to break, so unless I were to take a flying leap test onto his coffee table, it'll be alright. I also made some mortise and tenon joints out of oak of the same geometry and tested those, and those actually came out slightly stronger than the ones made out of aluminum, so the same geometry could be made out of wood and it would hold up about as well.
I'm going to show you how I made this coffee table out of walnut plywood, aluminum legs, and this cool lift top mechanism.